Hi everyone. Recently I read an article where very nicely they have explained how the first law of thermodynamics can be understood or how it comes from work-energy theorem. It's not a derivation, it just basically explains what are the things we need to include in work-energy theorem, what are the new things which thermodynamics includes in work-energy theorem in order to get the first law of thermodynamics. Now, before we jump into it, let us quickly discuss what is work-energy theorem. So, work-energy theorem says that if you have a system, right, there may be many particles inside the system or many parts of the system, right? And let's say there are some external forces from outside. It could be gravity, it could be normal force, right? It could be frictional force from outside. And there may be some internal forces between these particles. Some internal forces, which could be the electrostatic forces between the charges, or it could be some viscous force. Let's say there are some fluids inside. So because of rubbing between the fluids, there will be some viscous force, frictional force kind of thing, right? So whatever forces are acting external, internal, the work done by all the forces acting on the system, all the forces, that is equals to the change in kinetic energy of the system. So this is the main idea of work-energy theorem. Now here all the forces means work done by external forces plus work done by internal forces. Let me write only Ex, and that is equal to your change in kinetic energy of the system. Now how to write kinetic energy of this system which has particles inside? Well, if all the particles are moving with same velocity v, then kinetic energy will be simply half into mass of the system into v square. So if all the particles move in a very ordered way, meaning they are all moving together, okay, with same speed, then kinetic energy would be simply half mass of the body into v square. Now generally if you have a system, okay, all the particles will not be moving with same velocity, isn't it? Different particles may move with different velocity, right? So now to write the kinetic energy of this system, we have to write individually the kinetic energy of each particle, right? Half m1 v1 square, half m2 v2 square, and so on. However, there is a simpler way to think of this kinetic energy, and we can divide this into the whole kinetic energy into two parts. If you want to know the derivation of that, then please let me know in the comment section. I will show this derivation of this equation which I will write here in the next video. So what we have to do is we have to consider this motion as made up of two parts. One part is all the particles are moving with same velocity, same as the velocity of center of mass. Okay, so there will be a point called center of mass which is moving with some velocity. When this system is going forward, there will be one point in that system which is moving with some velocity, right? When you walk, your center of mass is moving with some velocity, isn't it? But different parts of your body may not be moving with the same velocity. The hair, the fingers, so they may not be doing the same thing as the center of mass, isn't it? So when a body is moving, the center of mass is moving with some velocity vc, let me write. But other particles may be doing different things, right? So to write the kinetic energy of this system, there is a simple way to think. You have to think of this complex kinetic energy is made up of two parts. One part is the simple kinetic energy where all the particles are moving with same velocity. So this is your ordered kinetic energy. Ordered, matlab all of them are moving together. So what would be kinetic energy of this part? That would be half into mass of the system, because all the particles are having same velocity. So it will be mass of the system into Vc square. Okay, so this would be the kinetic energy of this system. Of course, these two systems are not same because this is completely ordered. Here, there is some orderedness. Of course, the system is moving here, but there is some disorderedness also, right? Disorderedness in what sense? The different particles are moving in different directions. So, obviously, this system is not same as this system. But this system can be shown to be this plus. You have to assume the center of mass is at rest. Okay. And with respect to center of mass, you have to see what are the velocities of the particles. Okay, V1, V2, but all these are relative velocity. V1r, V2r. What is V1r, V2r? Velocities of particle 1, particle 2 with respect to center of mass. Since I said with respect to center of mass will be taken to be at rest, no? So the kinetic energy of this system, that I will write as chi K internal. Now, why am I calling this kinetic energy as internal kinetic energy, which this system has? That's because this kinetic energy, which this system has, is obviously external, because I am saying here the center of mass is moving with some velocity. And if I see the center of a system is moving, I am observing it from outside, isn't it? But here I am saying center of mass is at rest. So these are the velocities of particles with respect to center of mass, which is a point inside the system. Therefore, this kinetic energy is with respect to something internal to the system. And therefore, this is your internal kinetic energy, right? So, if your system is simply at rest, let's say there is a container which is at rest, so its center is not going anywhere, but you know the molecules of this air inside, they are moving around, right? So this system also has kinetic energy, but not because of this. This kinetic energy is 0 in this case because center is at rest. So Vc is 0. But because particles have velocity with respect to center of mass, because they are moving, so there will be internal kinetic energy. Okay. So after understanding that point, I can write work-energy theorem as work done by external forces on the system, work done by internal forces on the system is equals to delta K external plus delta K internal, right? Okay. Now the forces here which are doing work, whether external or internal, can be divided into two groups. One is conservative force and the other is non-conservative force. Conservative forces are those for which the work done by conservative force can be written in terms of potential energy. Okay, the formula is minus of change in potential energy. Again, if you want to know the derivation of this, you have to let me know. Okay, otherwise the video will become too long. So this is something in class 11 you learned. So work done by conservative force is minus of delta U. Conservative forces are like gravity, electrostatic force, spring force, right? And for all these forces, we have a potential energy, isn't it? For friction, you have never heard potential energy, right? Because friction is not a conservative force. So we will now write this work done by external force as work done by conservative forces which are external and work done by non-conservative forces which are external. Okay, so this could be due to gravity, conservative, and this could be due to friction from outside. Okay, similarly, work done by internal force can be also divided into work done by internal conservative forces, which could be electrostatic force, for example, and work done by internal non-conservative forces, which could be viscous force between the fluids. Okay, if you consider, let's say, human body as a system, right? So there will be fluids inside and the viscous forces will be non-conservative. So that would be equal to change in kinetic energy external plus change in kinetic energy internal. Now I told you work done by conservative forces can be written in terms of minus of change in potential energy. So this can be written as minus of delta U external, remember, and this is also conservative work done by conservative forces, right, internal. So this can be written as minus change in internal potential energy. So this would be the potential energy between the particles within the system, because there may be some interaction between them. So that will also give you some potential energy. And this is the external. For example, your system may be interacting with Earth, which is outside the system. So because of Earth also there will be some potential energy, that is this. Okay. Now this equation can be written as work done by external forces which are non-conservative. It could be applied force from outside, right? Pankaj sir's force is non-conservative. And work done by internal forces, non-conservative, like frictional forces, viscous forces between the layers of liquid. That would be equals to change in kinetic energy external, take this one that side, plus change in potential energy external, plus change in kinetic energy internal, this term, and then take this minus delta U that side, plus change in potential energy internal. So this is where we have reached, okay, work energy theorem. Now let's try to understand what this equation says. This equation is saying that by applying non-conservative forces, let's say by pushing the body, or frictional forces are acting, let's say, from outside, or because of some internal mechanism, some internal forces which are not conservative. So because of work done by external forces or internal forces, there can be change in what? Kinetic energy and potential energy of a system. So by doing work, we can change kinetic energy or potential energy or both of the system, isn't it? This is what this equation is saying. Now focus on this part. Work done by external forces which are non-conservative. Now this force can be written as integral of the force which is applied, the external force, and the small displacement, right? Technically, if I say, I have to put dot product. This equation is something which you guys already know, right? Force dot displacement is work done. Then integrate to find total work done. Now this F is the force which is applied. Okay, it could be the frictional force, or it could be me pushing the body. So this is a macroscopic force. It can be measured, 5 Newton, 10 Newton, right? For example, you take a system and let's say you want to change kinetic energy or potential energy of this system. Then till now what we learned, we have to apply a force, a macroscopic force, and do some work, and that would change the kinetic energy or potential energy of the system, right? Internal or external. Now thermodynamics says that you don't have to apply only macroscopic forces to change the energy of the system. There is another way to change the energy of the system, and that is through microscopic forces. How? Well, what you can do is, instead of applying a macroscopic force and doing a work, what you can do is you bring in contact to this body another body, okay, which is hotter than this body. Then what would happen is, the atoms of this hotter body would collide with the atoms of that system, and that is how, through collision, there is a possibility that the energy of the system will change. But obviously, to calculate that energy change using this work done, this formula would be very difficult, because there would be so many billions of forces, right? Microscopic forces acting on the system in the atomic level. And therefore, we will not be calculating that energy given through this work done. we will be calling that a separate term, and that separate term is what they call as heat. Okay. So besides the macroscopic force doing work and changing the energy of the system, thermodynamics says there is another way, and that is by supplying heat. And how to bring heat into this now? Well, the work done by external force, non-conservative, can be written as the work done by macroscopic forces, non-conservative, but macroscopic forces, applied forces, frictional force, whose formula you know, right? Plus the heat supplied, and this is basically the work done by the microscopic forces, which cannot be calculated using this formula because there will be billions and billions of forces. So to measure this, we have to find some other concept, right? So we learned that this can be written as two parts: work done by macroscopic force, whose formula we can write as integral f ds, and thermodynamics included a part called heat supplied, isn't it? Now this I will take that side, so it will become delta k external plus delta u external plus delta k internal plus delta u internal plus, or I should say minus, when it goes that side, work done by internal non-conservative forces. Now you can notice that these three terms have something common, right? And these three terms are associated with what? The internal constituents of the system. So this is the change in kinetic energy of the molecules of the system, change in potential energy between the molecules of the system, and this is the work done by the internal non-conservative forces. So in thermodynamics, we write this as change in internal energy of the system. So let me write it as capital I. So capital I here means internal energy of the system. So this equation can now be written as work done by the macroscopic force. This is the heat supplied, and this is the change in the kinetic energy, external, change in the external potential energy, and this whole thing thermodynamics says we can write change in internal energy of the system. So this is your most general form of work-energy theorem with these new concepts of heat supplied and internal energy. Now in thermodynamics, we usually consider cases where the external kinetic energy or potential energy doesn't change. So it could be a gas in a container at rest. So since it is at rest as a whole, the center of mass will not move around. So the change in kinetic energy external will be zero. And if you don't move it up and down, or if you don't connect it to any spring and all, then there will be no change in potential energy of the system also, external. So in that case, work done on the system by the macroscopic forces plus the heat supply will be equal to change in internal energy of the system. And this is what you all know as first law of thermodynamics. The only change is we usually in thermodynamics write internal energy as capital U and not I. That is because I wrote capital I because I used capital U for potential energy, right? In mechanics, we use U for potential energy. But in thermodynamics, we write U for internal energy of the system. So just keep track of the symbols, right? So this is how first law of thermodynamics can be understood from work-energy theorem. Now in physics thermodynamics, we change this W to minus W, and then we write Q is equals to delta U plus W. Don't get confused, it is the same thing. The only difference is here if you use this equation, then here you have to consider work done by the system as positive. And if you write this, then you have to consider work done on the system as positive. Because this W, it came from this W, right? If you see. And this W came from the work energy theorem. And there in work energy theorem, what is the statement? We say work done by the forces on the system is W. So W means positive W, right? So there we write work done on the system by the forces as plus W. Whereas in physics thermodynamics, we write work done on the system by the forces as minus W. So when you jump to physics thermodynamics, you write minus W here, and then if you take it that side, it will become plus. So remember, this W is work done on the system or on the body by the forces, like we write in work energy theorem. And here in this statement, W is work done by the body on the outside, whatever is there on the outside. Here this was work done on the system by the outside forces, right? Okay. So just the small change you need to remember.